then today we'll start with the PyTorch example as an implementation of the policy gradient method. So let me connect. So we'll be looking at this slides. Oh, no title. So I want to create a non-trivial, interesting environment that is not too hard to solve for the policy gradient algorithm or other reinforcement learning algorithms. And looking at the domains that we have investigated so far, we started out with tabular approaches where our entire environment could be represented easily, not easily, but could be represented using a table either of the value function or Q values. But now we're moving into domains where this particular table will be prohibitively large because the state space is enormously big, or the state space may actually be continuous and thus have an infinite number of states. So I want to design an example with a continuous environment. And this is what I came up with. So we have a robot that starts at location 0, 0, and it has to reach the green goal location at 1, 1. To make it a bit more interesting, we have two doors in our domain that the robot can go through, and otherwise the blue walls. So the robot cannot go through the blue walls, has to go through the door here and then through the door there, and then it can reach the goal location. And we can create different ones, right? But it's always these 3 rooms. Let me try and find a quite so extreme where they're a little bit more in the center. Okay, let's take this one. Wait. So we need to check what actions our agent can execute. So similar to the grid world, we support up, down, left, and right motions. They can be executed, and now it becomes a little bit tricky to implement it and to step through the environment. So every time the robot moves now, there is a noise that is added to the motion. That's how we end up with a continuous state space. And I needed to add extra lines because it actually then turns out to be a little bit more tricky to implement the movements of the robot. So we have a function step that passes in an action, the current robot location, the environment, the distance that we want to travel, the noise, and the padding that is applied to the doors. And that's just because if the robot is at this location here, it cannot go through the door, and we need to make sure that doesn't happen, right? Because if I'm here and I say move 20 centimeters, then the target location will be there, but the robot will have teleported through the wall there. So we have to make sure that the robot cannot do that. So I implement a routine to check if 2 line segments intersect. One line segment is from x1, y1 to x2, y2. The other one is from x3, y3 to x4, y4. That basically means that you need to solve a system of linear equations in order to identify if there is an intersection between those 2 lines or not. And I extend the lines to add some extra padding to detect if the robot is close to the wall or not. And we specify a reward if the robot is int p. If the robot hits a wall, there's a penalty of 1, so -1. And if we're less than 0.1 away from the goal position, then we get a reward of 1. That's what we return. So the random policy simply selects a random action 0, 1, 2, 3 for what was it, left, right, up, down, left, right, 0, 1, 2, 3. So our random policy doesn't care about anything, it just picks one of the actions at random and then it'll execute it. So then we can evaluate the policy. Oh. So then we go through a bunch of positions. Steps in this case, and then we can trace the policy. So here's our robot running around randomly. It's now trying left, up, right a lot of times, so it hits the wall all the time. Now it manages to go up there. Not surprisingly, it's not doing very well going towards the goal location. But as you can see, there's no, it's not like in the grid world where we're moving through one cell and then the other. The positions are actually the positions that are distorted by noise. So then, what I need to do in order to solve that domain, given that I can only move right or left, up and down, is we're looking for the Manhattan path from here to there, going through the 2 doors, and then ending up in the goal location. So with just right and left position movements and up and down movements, how do I follow a particular target location? Now, if there's no obstacle in my domain, then it's pretty simple. So we get the current location of the robot and location of our goal, and then we look at the difference in X and the difference in Y for those two. And distance is the distance that I want to move with every command. And then we just check if our difference in the Y coordinate is bigger than the difference in the X coordinate in an absolute sense, and then depending on which direction that goes, we simply go either up or down, because dy would have we need to make more steps in the Y direction than in the X direction, otherwise we choose to go right or left. Then I can append the actions, and then that will return the plan in order to reach the goal location. Now this is now only in an empty field, not with the doors. So to find the optimal path, I now simply have to check which room I'm in, right? If I'm in here, I need to find the Manhattan distance path from my current location to this door. And then from here, from this door to that door, and then from that door to the goal. There's no shorter way to do that. If I'm already in this room, then I only need to go to this door and to the goal. And if I'm already in this room, then I simply go straight to the goal. So that's what this code does. So it checks if my X location is less than the location of the horizontal wall, the vertical wall, and the goal location is on the other side, then I extend the path, I find the Manhattan path to the location of the door. And so HV is the vertical wall coordinates and HH is the horizontal wall coordinates. If I'm in room number 2, then I find the location from the current position, which would be the door in the previous case, going through the horizontal wall, and then from that location towards the goal. So here's our new select action routine then, which simply picks either up and down action or left and right action, depending on which one has more change left. And then this would give us our optimal policy. So now for any location, I can tell the robot exactly what it should do. So our reinforcement learner doesn't know this, right? The whole point of the reinforcement learning is to learn this function rather than reasoning about it and implementing it. So now we found the optimal path and an animation, so now my robot can start. And now the last one is not drawn, but now it's close enough within 0.1 of the goal location. So it solved the problem. And of course, this is much better than the random policy. So from a reinforcement learning point of view, we now have this optimal policy. The only reason why I implemented the optimal policy like that is so that we can sort of see what the system has to learn, what we're trying to learn, and how close we are to learning the right function. So I'm going to calculate the value function for this domain. I simply break it down into different areas, pick the center point, and then check what reward I would get by executing this optimal path. And then that's my value function. So I generate all the coordinates in X and Y, and then go through each one of them and either set the value to minus 1,000 if we're in a wall, if it's a wall location that the robot can't reach. Otherwise, I find the optimal path, and then because we get optimal path doesn't run into any walls, and it will receive 1 at the very end, so the valuation would be gamma to the power of the length of the path, because we want to decay by gamma and then append that value to the row and build up the table that way. And here is a heat map, a 2D representation, colored 2D representation of the value function then. This one I want to bring down. And then this is the resulting heat map for that particular domain. As you can see, there's a big gash here in the colors, right? Because if I go up there, in theory, the color should decrease, should be closer to yellow, should move towards the yellow, but the door is down here, so the further up I go there, the more I have to move. Because I have to go down here where the value actually changes from the reward maximizes here, so this is where the doors should be. Then I go through and the other door is over on this side. Actually, to have it against would be better. Yeah. And then this is the value function for this particular domain. It's how many steps I need in order to reach the goal location. So let me see if we change the domain. That should be interesting. Goal 1, 1. So this is the padding. HX, HH1. So I'll change G to be HV 0 plus 0.3, and that will be the x coordinate and y coordinate 1.0, and that should be a tuple. So we can now try only draws it up to so we draw the environment. So it's drawing the that draws then. And let me cut this into 2 slides. Okay, I'll come. Now we have this domain. the robot. And then why did that stop now? So find the optimal path and current location 0, 0, distance 0. And here's our environment. One, two, three, four, five, six, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So then let's see if we have 0.3, 0.4. So now we're starting here. Now we get there, okay. And here I was at 0.6, 0.1. It takes a while to draw. Cannot go through this door anymore because I think it's stuck with the padding. But it finds the optimal path. That's weird. So find the optimal path for these values is wrong one. Find the optimal path. Oh, I think the policies messed up still. So here's the optimal path, and here's the step optimal policy. So optimal policy, robot, if there's graded comics. So we can check which branch we now have. Still So he wants to go up. But why is it not going up? So Rx minus HHX for width over 2, Ry greater than HHY. Option up. So step action up. Oh, that's so I cannot teleport through the goals either. So this should be 1.0 here. Rx, Rx, intersect line. some reason it won't, GY. 0, 1, 2, 3. Okay. So now we can plot our curves. But now it went to the target location, so why? Oh, because I didn't draw the animation here. Okay, I don't want to draw it from 1, 2, start at 0, 0. Right, so this is our optimal Manhattan path now. It's only right, left, up, down, so we cannot go diagonally. So that means it doesn't matter if it goes left, left, up, left, up, left, up, left, up, or up, 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 left, up, left, left, up, left, up. If you add all of these together, then the sum of the line segments is going to be the same. So now let's draw the value function. And then this is what we get. So here you can see the discrepancy or the break, the discontinuity in the value function due to the vertical wall. And down here, not so easy to recognize the discontinuity due to the horizontal wall in the environment. So this is what we have here. So now our goal is to generate, to train the system to learn exactly this value function here. So I added a function to draw the training data, and then first we can think about using a linear approximation, linear regression function, in order to approximate our weight, our value function here. So instead of as a table, I now want to represent it by a function, and that function, that problem then is called regression. So one of the most common algorithms for solving that kind of problem is to use a linear regression. So I can define a function based on a set of inputs in order to generate what the correct value function should be. And the linear regression is one way of doing that computationally very quickly. So our input will be the x and y coordinate, and the output should be the value function. So then the question is, what kind of model do you want to use? Now if I just use x and y, directly, then my value function has to be of the form v is equal to theta 0 multiplied by x plus theta 1 multiplied by y. Okay. Or, because we have a two-dimensional domain, then it's natural to think about x and y. Okay. But in machine learning, we're often dealing with high-dimensional spaces. So in that case, we call all the features, all our inputs x. So this would be x0 and x1. So I could also write it like theta 0 times x0 plus theta 1 times x1. Those are the same thing. And how do we solve that particular linear regression problem then? So now it's a supervised learning problem, right? So now I give you a set of coordinates. Let me give you a set of coordinates, and then you can think about that. What did I call my function? So I think that's correct. And then random V. Gamma is not defined. So here's your training data, and calculate the linear regression for this training data. So x and y is what your input is, and theta 0, theta 1 is our weighing factor. And I have to go to the washroom. So, what are the parameters? Theta 0, theta 1 for this linear regression problem? Or why is it called a linear regression problem? How do we convert this into a system of linear equations that we can solve? What? Four equations? How do you get four equations? Right. Yeah. So I can write this as 0.65 multiplied by theta 0 plus 0.85 multiplied theta 1 is equal to V, which is 0.21. And the other equation would be 0.24 multiplied by theta 0 plus 0.97 multiplied theta 1 is equal to 0.07. 0.7 theta 0 plus 0.78 theta 1 is equal to 0.28. 0.45 theta 0 plus 0.23 theta 1 is equal to 0.21, and 0.76 66. Okay, that's exactly the information that I've stored in that table. So now I can convert that into a matrix equation where I have one matrix here, theta 0, theta 1 is equal to this matrix. Right? So that just reads exactly the same using matrix multiplication. So 0.65 theta 0 plus 0.85 theta 1 is equal to 0.21. Now I'm trying to figure out what is theta 0 and theta 1. So implement a Python program that can solve that. How would you solve that using Python?
I think I would just use the versus
I don't even know why you would use 3.
yeah, no,
How many unknowns do we have? 2 unknowns, right? So how many equations do I need to solve it? Usually I would only need 2 equations. The problem that we have here is that we have more than 2 equations. So we have, in theory, we have an over-constrained system, right? But in fact, that's not quite true, because these points, we can assume that there's some noise associated with it, right? So then we can take that system and say we want to calculate the least squared error approximation to the solution. So then I turn this into an optimization problem where, because if the numbers would be all exact, right, no rounding errors, no problem, then the two equations would be sufficient to find out what theta 0, theta 1 is. But because there is noise in the data, we won't find an exact solution. So what we want to do is we want to find a solution that has what property? And I'm sure from high school you remember this picture. You have a bunch of points. And now you're trying to map a line to it. Then what line do you want to map? Where these two problems are exactly the same, except here we only have one variable, here we have two variables. So if I have a data set like this, and I think it's a line, then I want to map a line through there. How about this line? That one wouldn't be good, right? You'd think this one would be a lot better, right? And why? Yeah, it minimizes the square of the error. So for our least, that's why this is called least squared error approximation, right? Not surprisingly. So what we're trying to optimize is we want to find the minimum theta 0, theta 1, so that so if I write it long form, then it will be x. What I calculate, right, is x0 multiplied by theta 0 plus x1 multiplied by theta 1 Now that's what I calculate, right? This is what the model would predict, given parameters theta 0, theta 1. This is what I would get, minus, and now I subtract v1, not v, the v, vi, and this one here would be xi1, xi0, and we sum up over the x's, and we square this. Right? So in Python, this is actually, I mean, do you know what the solution is? I mean, if we only have two equations, then how would you find the solution to a matrix equation like that? Ax is equal to b, where all of these, this is a vector and this is a matrix.
You multiply so that
multiply what?
You multiply by, you have, so you're gonna have B1 equal to, BK0.
Yeah, so this matrix here is A, right? This matrix here is usually called B, so I can write it in this form. Then I can pre-multiply by A minus 1. Which will then, this will be the identity matrix, so this gives me theta is equal to A inverse B, right? But this only works if A is a 2 by 2 matrix in this case. Right? Now my problem is A is not a 2 by 2 matrix, but it's a n by 2 matrix. So we use what's called the pseudo-inverse method. By a Moore pseudo-inverse method. And this is actually a pretty cool trick. You should definitely always remember this one or know how to do this one. Because if you understand this, you understand you basically understand most of the machine learning algorithms. So the pseudo-inverse method, this doesn't work because the inverse doesn't exist for a n by 2 matrix. But the least squared error approximation, this value I can actually get by calculating the transpose of A multiplied by A multiplied by theta is equal to transpose multiplied by B. Right? And if I do that, then A is a n by 2 matrix. A transpose is a 2 by n matrix. So AT multiplied by A will be a 2 by 2 matrix. Multiplied by theta, this will be n by 2 multiplied by, 2 by n multiplied by n times 1, which will be a 2 by 1 matrix. So then I have a 2 by 2 multiplied by theta is equal to a 2 by 1 vector. So the dimensions all work out correctly. And in fact, that is the solution to your least squared error approximation. If you solve, now you have a new system of linear equations. If you solve that problem, the answer that you get for theta will be the answer to the least squared error approximation. So to go from a normal n by n linear system of linear equations to solve the least squared error approximation in case of an over-constrained system, you simply need to pre-multiply it by the transpose of your matrix A, both sides. And in fact, that's done already in Python. Not in Python, in NumPy. So NumPy lin algebra has a lin squared function that will do that for you. Or you can, of course, you can just implement that by hand too using NumPy. So A is equal to So the solution is np.linalc dot, I think it's called least squared, AB. No. Oh, least square. That's because I usually just and then here's our answer for theta 0 and theta 1. And it also gives you the, so x is the least squared solution, the residuals, which gives you the size of the error that you get. Singular value, I'm not sure why you would want to have those. If you're only interested in a solution, all you really care about is x, and the residuals are interesting because they give you an idea of the error that is associated with this approximation. So that's a standard, and LinSolve. LinSolve is the one that there's a tensor solve even now. Oh, it's just called solve. Okay. Here you get the two solutions and they're identical. So now let's see how that looks. So now we iterate over xs and ys and the solution. And that's my table now. Now I can plot it. T. Here's our approximation now, and let me see, drawing the function. I just want to make sure I use the right version. Yeah, so it's actually should be drawn correctly with V minimum from 0 to 1. And as you can see, our approximation is not very good right here. This is what it should look like. Now the problem is that our model is very restricted at the moment. I can only multiply x by something and y by something, right? So if I want to get a better result, then what do I have to do? to represent a surface like that, because this is basically three-dimensional now. The color tells you the height. So one problem is that if we use a linear combination, then in one dimension I can only draw a line. In two dimension I can draw a plane. But in a sense, I have no way in which, and then I need to, if I think about machine learning, then in the simplest sense, or in the sort of simplest case, I only have to distinguish between two classes, 0 and 1. Right? So my output, instead of having a continuous value function like that, I simplified. I just want to be able to distinguish between 0 and 1. And if my cases are like that, so red and blue, and my training data is like this. In the one-dimensional case, this is not a problem, right? Because I can separate all the reds from the blues by putting a line here. That would work. Right? Now, all the blues are on one side, all the reds are on the other side. So in this case, my training data is linearly separable. So the model is powerful enough to actually learn the target function correctly. Right? In our case, what we have now is, it looks more like this. So now, if I'm allowed to draw one line, then what line would you draw? It's impossible to separate those two. So in this case, the data is linearly not separable. So the solution to this in order to make it linearly separable is to have a more powerful model. Now, if I just keep adding extra theta 0 times x, if I now say, oh, I need more parameters, right? I only have two numbers, so there's no way that I can map that target function to just two numbers. So what I could do is I could have four numbers, right? So I extend theta. But if I do this, xy, multiplied by theta 0, theta 1, theta 2, theta 3, then I will not have gained anything. Because if I now write out the equation, I get x times theta 0 plus y times theta 1 plus x times theta 2 plus y times theta 3. Right? So now I have more unknowns, but the model is not any more powerful because that is the same as x multiplied by theta 0 plus theta 2 plus y multiplied by theta 1 plus theta 3. Right? So that's the same. I only have one number there. So I didn't really gain anything. So if I want to have a more powerful system, if I want to be able to, and these functions are called kernel functions, if I want to be able to represent a more complex target function, then I need to introduce some nonlinearity. Because the linear part is all solved using the system of linear equations. So now I can, but this works quite often, quite nicely. So here, right now I only have one dimension, just x, right? Now I convert it into two dimensions, x. And here I need to introduce something that is not a linear combination of x. So no k times x. That won't make any difference. So what can we do? Well, if you've taken my course on machine learning, then we would have talked about support vector machines, or many other machine learning algorithms. In fact, lots of other machine learning algorithms. They will use polynomial features. So here I map it to x and x squared. Right? So now my data becomes, from one dimension, I now map it into two dimensions. And I map it from x to x squared. So I would get x squared 0. 0 squared is also 0. Right? And then here I get this one and this one. And then these ones, these three, would be mapped to there. And then these ones, these two. So this should now be a parabola. Right? Because it's x squared, so it should be a parabola. So how does that help me? Because now, instead of having just a point here, I can now draw a line through here, like this. Right? And now, my data is linearly separable. So I can use the same algorithm, I can, but instead of just having x and y here, I also add x squared and y squared, which is just the numbers that I have, just square them. But by adding that, I now give more freedom to the model. It's the same thing as adding more nodes into your neural network. So to have a complex function like that, just using x and y, the model is too simple. So I need to come up with a more powerful model. Any other? In this case here, for this original example here, or our example with the value function? Any other ideas for a nonlinear function that I can apply that may be useful? Okay, let's look at that in a minute then. Once we get to it. Now, what I could do is I could just extend this, generate a larger A matrix, x, y, x squared, y squared. Then, in order to solve it, I would have to solve invert the matrix here. Now, matrix inversion is an n-cubed problem. So if we have 5 numbers, that's not a problem. It'll run in microseconds nowadays. But if you have a very large matrix, this becomes a problem. So for large scale problems with many dimensions, we usually don't solve it using this approach, which is what's called the normal equation approach, but we solve it by actually, there's a factor of 1/2 when I calculate when you write this as an error function, or in a neural network language, it would be called a loss function, right? Then usually you see a term of 1/2 there. And what I can do is, instead of calculating the inverse of the matrix, which may be potentially large, if I have a very large set of features, thousands of features, then computing the inverse is time-consuming and also sometimes numerically not stable. Then we run a gradient descent on the loss function, or on the error function. So gradient descent now means, because I'm trying to find the minimum of this error function with respect to theta. Now theta is, it's a multi-variable optimization problem. Right? It's a multi-valued function that I need to optimize. However, the basic tenet of calculus still hold. How do I know if I found a minimum? Yeah. If you do gradient descent, yes, then you could compare. But if you have any function, 4x cubed plus 2x, then you need to calculate the derivative, right? So here, we have a multi-valued function instead of a single-valued function. So if it's a multi-valued function, we need to calculate the partial derivatives with respect to theta 0, theta 1, theta 2, theta 3, right? So that means I need to take that, and I need to calculate the partial derivative of my error function with respect to theta 0, theta 1, which will be your gradient then, right? So we're trying to calculate the gradient of our error function. So we get the partial derivative. So that means I assume each one of these is fixed, except one of those thetas is a variable. And that's where the 1/2 here comes from, because in order to differentiate this, correct, so I have to differentiate this by using the chain rule, right? Because here I have a function of theta multiplied by xi, and then that whole thing is squared. So that means I get 2 multiplied by this function, post multiply the derivative of this component. Right? So that's how we get the 2, so then we add a 1/2 in order to cancel it. And the error function doesn't really matter, right? Because I'm trying to find the minimum of theta. Now, if I multiply my error by 2, the minimum will still stay at the same place. Right? Multiplying something by 2 will just scale everything in the y-coordinate by 2, but your minimum point, the x where you have your minimum, will stay the same. So that's the gradient descent approach. And for large dimensional problems, that's what we want to use. So what we get is then, for our derivative, it would be 2 multiplied by this, multiplied by, and then all of these are constant. All the thetas are constant, which means this is a constant, this is a constant, this is a constant, bi is a constant. The only thing that's not a constant would be the theta I that we're calculating. So we have to multiply by theta I at the end. So that's a gradient descent algorithm for solving least square error approximation problems. Now, I've implemented that also in the Jupyter notebook, but right now we want to use it in using PyTorch, because PyTorch is a very popular library for doing deep learning, AI, a lot of numerical computations, and also reinforcement learning. It's a library developed by Facebook AI Research, so FAIR, and I like it a little bit better than TensorFlow. But TensorFlow is also a very good library. JAX is another one you could be using. We'll just use PyTorch in this particular course. And I design a couple of features, extra features then. And I decided to use up to a third order polynomial. And this is really just a guess. I didn't put much thought into it. So we have x, s of x squared, s of x cubed, s of y squared, and I guess I cannot put in the last one as well, because there's only one missing, s of y cubed. So now we solve that linear regression problem using gradient descent. Our model is A, so some bias term, plus B sx, C sx squared, D sx cubed, plus E sy, F sy squared, G sy cubed. right? And that will generate our output here. So I wrote the same code twice now, or is that from the previous one? No, so this is the training data. We can generate. Okay, this is the least squared error approximation. We plotted. So now I want to use PyTorch. Now for this particular problem, it would be, we could just implement the gradient descent, right? And I could implement what the gradient is and then step in that direction, applying standard gradient descent algorithm. In PyTorch, however, it is pretty neat in the sense that first let me create the training data. So now I just generate how many? 250 of them. And the output. And here's the actual PyTorch program. So I could have written this as a single vector, but I wanted to make it explicit, so we have unknowns A, B, C, D, E, F, G, where it's A plus B times X plus C times X squared plus D times X cubed, plus E times Y plus F times Y squared plus G times Y cubed. And then for a given model, I initialize it randomly. I use random numbers. Now these need to be we need to use the PyTorch functions, torch, to actually generate them. Now, the nice thing about PyTorch is that it's pretty reasonable, or it's very efficient in the sense that you can send the computation over to your GPU. Now, the Google actually allows me to use the runtime, and we can check that later. But right now I'm just using the CPU. But if you have the CUDA library installed, then with PyTorch, you can just set that to GPU, and it will do all the matrix calculations on the GPU, which will be a tremendous speed up, especially if you can batch your computations. Then it will run 2 orders of magnitude faster than running it in the CPU. So I have the training data. Now gradient descent is a stepwise algorithm. Like here, if I solve the system of linear equations, I solve it once, boom, I have the solution. Gradient descent, we're slowly approaching the correct value because we get closer and closer to the solution, right? So I run 1,000 steps, maybe a little bit too many. I'll just run 100 first. So if I have a model, A, B, C, D, E, F, G, then the prediction of that model would be A plus B multiplied by the x values, multiplied by the x values squared, multiplied by the x values cubed. Oh, it should be, no, sorry. Train x, which is the x values, y, these are the y values. Now, that prediction, I compare that to the correct value. So I need to, it's a supervised approach, right, in this case. So I need to know what the correct value is, square it, so power of 2 is squaring it. So that difference, square it, sum it up, and then generate a number. And then I can calculate the gradient for the prediction as well as my parameters, A, B, C, D. And then I can take one step in that direction, and I use a learning rate, so I don't go all the way to, I take small steps in the direction of the solution. Every 50 times I print out the value. So you can see how the loss, the error, greatly decreases from 0 to 50, 739 to 16. I can run it some more steps. And this part here, that's exactly that gradient calculation, right? Except because in that case, my loss function, I didn't have the 1/2 as part of my loss function, so this is why that is 2 times the prediction minus the trained value. And these are the partial derivatives for A, B, C, D, E, F, G. And learning rate, let's increase the learning rate a little bit. And let's run it for 500 steps. Then you can see how we approach our solution, our approximation gets better and better. So then let's plot that function. So here our approximation is using cubic functions. Now, the circles are the actual training samples that I created. And you can see now the function already looks a lot closer to what our target function actually is than what we got with the simple model. This is our target function here. But I made a mistake. Create training data, go. So now before I didn't sample throughout the entire, I mean, there was a bug. Now you can see the circles with the color that would correspond to the training data and the value function that was actually learned by the system using gradient descent now and implemented in PyTorch. So there's also powerful functions for visualizing our networks or our solutions. Oh, yes. So now this is my function that this is what I get if I generate x squared, x cubed, y squared, y cubed. Right? That introduces nonlinearity. Now I have a more powerful representation. I get up with a much better approximation of the target function than if I just use x and y. But any other kind of function that I could use that may be useful in this particular domain? Like the problem, what we're trying to represent is sort of the three rooms, right? That's what makes this particular function difficult, I think. So it is not just a mapping along one line with different stretch factors, but in order to get the rooms, I think it would also be useful to have features that correspond x times y, or x squared times y, or x times y squared. The cross product. And I think because we're dealing with the navigation domain where we need to identify areas, I actually think the multiplication would be useful, probably would be useful. So now, copy that code and change it and include, well, to be fair, we stick with 7 parameters, but now instead of having x cubed and y cubed, we replace it with x times y and x cubed and y cubed. Let's do that. And then check and plot the output and see which approximation looks better. Or you can also calculate the loss in order to see which approximation for our value function, which one works better. Is it better to use x squared, x cubed, y squared, y cubed, or should we use x squared, x times y, and y squared, and x squared, y squared? So change the features and see what the performance of the gradient descent algorithm is for that particular formulation. Instead of just x squared, x cubed. Right now we have constant x squared So now we want to change it constant x squared, x times y, y squared, x squared times y squared. So to make it fair, we keep the same number of parameters. Because otherwise it sort of wouldn't be fair, right? Because I can add extra features. Then invariably, usually, my approximation, my loss is going to be reduced greatly on the training set. Because now I have more free variables that I can choose. Right? So the loss that I calculate over the training set is going to be much reduced, will be much better. But what's the problem with having a more complex model? It will follow the training data, but sometimes, not sometimes, very often, it will follow the training data too closely, which means that it will be bad at generalizing. And anytime we're dealing with a problem like that, the training data really is not important. The performance on the training data is completely useless. Because if I want to have good performance on the training data, then all I need to do is store all of that in a table and look up the value. Right? I could just store that in a database. The important feature is to be able to predict unseen values, right? And there's a extremely high danger that if you keep increasing the complexity of your model, your generalization ability will get worse and worse, because the functions that you calculate end up being too specific to your training data. That's called overfitting, and that's at the heart of machine learning. The ability to generalize is crucially important for a machine learning algorithm. If you're overfitting, then you have the illusion that your algorithm does better and better, because you end up with less and less error in your training data, but your generalization ability, the ability to predict unseen values, gets worse and worse. And so this is the problem in machine learning. That's why you cannot just build a neural network with, we could do this. I could build a network with 10,000 nodes. It would find the training data, it would map the training data exactly. But it would do a very poor job on the other regions of the environment. Okay, so now change the code. And this is trivial change. You can just change x and y here. So replace x cubed with x times y, and y cubed with x squared multiplied by y squared. And by the way, while you're doing this, how do you avoid the problem of overfitting? Less variables, yes. Restrict the complexity of your model somehow, yeah. That's one approach. But the problem then is, let's say you have a target function like this, and of course usually we're dealing with very high n-dimensional target functions, so they're difficult to visualize, right? So even if you can visualize like this, it's not clear to specify whether this should be a do I need to go up to x cubed, or x to the power of 5, or x to the power of 10? Right? There's really no intuition that I can look at this and I can say, oh, I think the correct model should be a degree 2 polynomial or a degree 3 polynomial.
Depending on what algorithm you get, the linear regression with the p-values, this is also
P-values. The residual values, but that's only on the training data. That will give you the error on the training data. No. What you must do anytime you have a problem like that is you have some training data, and what you must do is you must cut out some part of that and use it for validation. So that you train the algorithm on this, and you validate the algorithm on some data that you have not shown to the system in order to be able to evaluate how good it is at generalizing. Now there's different concerns, different issues that you need to be aware of by doing this. So one popular method is to use n-fold cross-validation, 10-fold cross-validation, for example. 10-fold cross-validation, you take your training data, 1,000 instances, you break it down into 10 buckets. Each bucket is 100 examples of training data. Then you train it on 900, you leave out one bucket. Then you evaluate the performance on that one bucket that you left out. That's the only number that matters. How good your algorithm is on the 900 that you tested before is completely irrelevant. The only number that matters is how well does it generalize to the unseen instances. And then you run that 10 times, you average those 10 numbers. That's a pretty good approach. If you don't have millions and millions of training data, this is a very good one. But there are some subtle problems with it, in particular easy to introduce bias. So the training data, when you get it, it's usually not in random order. Like when you look, my algorithm here, I go through the array from 0. I go this way. Right? If you look at the algorithm for generating the training data, oh, actually I don't. I thought I did. I actually don't. I picked some random numbers. But let's say I went through line by line, and then you cut off the bottom part, you always get the points that are high on the y-axis. They may or may not be representative of the kind of problems that you have to solve in general. Right? And that's a huge problem in machine learning and AI at the moment. In particular, for example, when training systems for face recognition. If you have a lot more picture of white people, then the algorithm is going to be, and you evaluate it on its quality, on its power to correctly identify white people's Caucasian faces, then your algorithm may do poorly against black people or Asian people. And so that's a very hard problem to actually deal with in order to, because it's virtually impossible to have completely unbiased training data. The other problem would be if your training data is heavily skewed. If you implement an algorithm to detect terrorists, then the problem is that you can look at millions of people, right? And out of 1 million people, let's say 10 are hardcore terrorists. So then your algorithm is doing 99.999% correctly by just saying nobody is a terrorist. Just because there are so few terrorists. Right? So in this case, your data is heavily skewed. That's also terrible. The basic assumptions of machine learning are broken in this case. Yeah, then you have to come up with tricks, so then you have to duplicate them. All kinds of things you could be doing. But the point is, often we're not aware of the biases that we put into the generation of our training data, which means that we don't think about correcting for them. And that's a problem then. Of course, once you identify a bias, then you can start thinking about methods for removing it from your training data. But unless you realize that your face detection algorithm cuts off all the black people faces, or people from Asia are recognized much lower, with much lower accuracy than Caucasians, you wouldn't think about changing your training data. With hindsight, yes, you can fix these things, but extremely difficult to do before now. Okay, so now let me see if you finished your x times y. Yeah, so you just need to copy those cells. You can put them, you can make a copy. You can copy this notebook. If you copy this notebook, then you can change it. To copy it. Save a copy and drive. You don't have that? Not sure. You should be able to make a copy. copy the notebook. You just have to log in with your Google account and then you can copy the notebook. Say again?
Also, asking them if you said you replace the exploit with Google and do the execute.
Yeah, you want to replace X2 with X multiplied by 1. And see if that performs better, worse, or the same as X So here's our x times y version. The changes are pretty easy. D must be multiplied by x times y, and G multiplied by x squared times y squared. And we have that, and if I can then plot it for the training, it's the same deal here. And this is our prediction, so the prediction is also dx times y here, and x squared times y squared here. And then we can apply gradient descent. In this case, I ran it up to 500, let's run it up to 1,000. On the training data, now I have a loss of 0.09, and I can plot it. And it seems to definitely take out this part better on the left-hand side here, where the wall is. This one here is a little bit hard to see, but if I look at the error, it's not that much difference. This one works slightly better, 0.09, as opposed to 0.11 on the cubic function. So we can use other kinds of, any kind of feature and then calculate the linear combination of those. Now, we can also implement a neural network, because a deep learning neural network as well. So here I set up a small one, let's say 16 nodes. So from x and y, I now generate a neural network which feeds into a hidden layer of size 16. They use rectified linear units, and then 16 nodes in the hidden layer are combined into or connected to a single output. And I also have a predict function, so given the state of the network, this is what I would get as the output. And you can also implement that in PyTorch. It has a nice function to actually draw your network. Now the training here works in batches. So I usually 0.9, especially because you want to patch it onto the GPU. So we're creating more training data here for X and Y. And the value function, I define the optimizer that I want to use. Either atom or stochastic gradient descent are popular choices. And then we can just train our network on that. 40,000. And my learning rate seems to be rather small. Let's speed it up a little bit. Oh. So here our network doesn't do such a good job, right? Because I only gave it 16 nodes. But I think you can try an experiment. How would you try and improve the performance of the network approach? Well, in this case, I made it really hard on the algorithm, right? It has to learn a lot more than the linear approximation, because the linear approximation, I told it that I'm interested in x, y, x multiplied by y, x squared, y squared, right? Right now, for the network, I just have two inputs, and if x squared is really useful, the network somehow has to work out a way to calculate this internally. And it has to learn that that particular value is even useful. Right? But it doesn't have enough nodes to do that, or enough layers to do that, I believe. So a fairer comparison would be to train the network with 6 inputs, like x squared, x cubed, y squared, y cubed. Because the network all have a bias term already, so I don't really need a constant. But if I want to, I could add a 1 there. That would be a fairer comparison. But we can also try and see if deep learning is powerful enough to do a better job learning this particular network. If I change this to a very large number here, 1024, I actually don't think this will result in a better performance, but we can try. So now I change the network. Instead of 16 nodes, I now have 1,000 nodes. But the problem is they're only fed from x and y, so they're sort of all going to change in lockstep. So let's see. Before our error was pretty bad, it was 40,000 or something. Now it's slowed down. $38,000, so I think didn't really change that much. Yeah. So also bad. So then until next class, you can figure out how to change the network structure and feed in x squared, these kind of variations. Or you can try and add an extra layer here. So now we have two layers. So instead of 1,000 nodes, I only have 32 now, but organized in two levels. Let's see. Slightly better. But not much. Point zero five. Okay, good. Then that's it for today, and next week we'll look at the reinforced algorithm, which is the pretty standard policy gradient algorithm at the moment, and we'll look at its implementation in PyTorch. Okay, good.